Yesterday we looked at how to solve equations that were exponential equations, and we used the property of equality and we used logarithms to be able to solve exponential equations. So today we're basically doing the reverse of that. We're going to look at equations that contain logarithms. And just like the exponentials had a property of equality, logarithms do as well. So what this says, the gist of it basically, is that if I know that the log base b of x is equal to the log base b of y, then x has to be y. Log base 2 of 5 is only going to be log base 2 of 5. They have to come out to end up being the same exact thing. So just like this example down here, if I have that the log base 2 of x is equal to the log base 2 of 7, then x has to be 7. That's the only way that I can make that log base 2 the same as the other side. And so, just like we said yesterday, we're not going to cancel out the logs, but we're using this property to tell us what relationship we can use. And so what the property says is that if they're both the same type of logarithm on each side, which in this case they're both natural logs, the relationship that we know is that 7x minus 4 is equal to 2x plus 11. The logs didn't really cancel. We just used the property to be able to know that the stuff inside the logarithms has to be equal to each other. So then I can add 5 to both sides and subtract 2x from both sides, and I get 5x equals 16. So x equals 16 fifths. And that's it. That's really all there is to it. So if we look at the one on the other side, they're both log base 7s, and the logs are both by themselves. If they're not, we have to do something a little bit different. We're going to save that for the next time I see you. But since the logs match, once again, we can set up the equation with the stuff that's inside the logarithms. So go ahead and check and see if you've got this one set up correctly. Pause the video and see what you get. So the equation that you're going to set up, you're just going to take the stuff out of parentheses there. 2x plus 9 equals 4x plus 6. I subtracted 2x from both sides, and I subtracted 6 from both sides, and that's how we get that x is equal to 3 halves. So those are the simple ones. If you have a log on both sides of the equation, you're going to set them equal. You don't have to change the bases or anything like we did with the exponentials. They're just going to match. So you just pull the stuff out and set them equal to each other. Now, if you don't have logs on both sides, you can't use the property of equality. And so if that's the case, we're going to do just like we did yesterday. We're going to work as far as we can to get the logarithm by itself. And then when we get to where there's nothing left that we can do, we're going to go ahead and rewrite it in exponential form. So for example, on A, the x minus 6 here is in parentheses. So this is all one term attached together. It's the log base 2 of x minus 6. So in this case, the logarithm is already by itself. Now, side note here is if the parentheses were not there, and I just had the log base 2 of x and the minus 6 was afterwards, the first thing we would have to do would be to add 6 to both sides in order to isolate the log base 2 of x. Because without the parentheses, the minus 6 is just a constant after the logarithm. So, since the log is already by itself, there's nothing else that we can do. This is just like yesterday. We're going to rewrite it in its opposite form. So once again, when we go from log to exponential, the base is the base no matter what. So that means it's going to be 2. And then remember that logs equal exponents. So the exponent I'm going to use is 5. And then the leftover piece is what goes on the other side. So I get x minus 6. Now remember, the whole point of rewriting it is so that we can get the x out of the logarithm so we can solve it. So that should always end up on the opposite side of the equation. And so now we just work this out. 2 to the 5th, again, that's not 2 times 5, that's 2 to the 5th. And that gives us 32 equals x minus 6. So lastly, we'll add 6 to both sides. And we get that x is equal to 38. And that is that. If you substitute that back in, 38 minus 6 is going to be 32. Does the log base 2 of 32 equal 5? And it does, because 2 to the 5th equals 32. So you know that you're on the right track. B is real similar. The log is already isolated. So once again, I'd encourage you to pause the video and see what you get after you rewrite and solve this one. So once again, the base is 4, so the base stays 4. Logs equal exponents, so that's why it's 4 to the third. And then whatever you're taking the log of gets to come to the other side of the equation. So you should be getting 13 after you solve that equation. Once again, just a reminder, 4 to the third is not 4 times 3. That's 4 times 4 times 4. So it's 16 times 4, which is 64. And so that's really all you're going to practice today. So just like yesterday, if you notice the difference between the two types of equations, this had matching logs on both sides, and these only had a log on one side. So if you only have one log, you want to get it by itself and then rewrite. You can't really do that here. We can't rewrite both sides on these where we have one on both sides, because I would write e to the natural log of 2x plus 12, which would work, but you'd have to know your inverse properties really well, and you're going to make the problem way harder than it needs to be. So that's the end. You have an assignment on big ideas, more than likely, so check that out. And I will see you guys when I see you.